My finger is even not working. Okay, let me get started. So image sensors are everywhere. They are used for a variety of purposes. So I'm just showing a few here. They are used in your autonomous cars. They are used for surveillance. They are used in medicine. They are there on your cell phones. They are sent to space to take images of the space. So let me start by going over when image sensors work well and what are the places when they start struggling. So here I'm showing a few images taken over a range of light levels, going from 250 lux to 25,000 lux. And you can see at these light levels, the cameras work really well. You can see that the details in the scene are mostly preserved and the images look really good. However, when the light level starts going down, we will start having an issue. For example, when I go from 250 lux to 25 lux, the image starts looking a little darker. I'm not sure if you can notice it on the screen, but you can add that is actually a very little noise. You probably need to use a slight denoiser to make the image look a little better, but then the image generally looks okay. It is not too bad. Now, if I go another order of magnitude down to 2.5 lux, the image you get looks totally dark. And you can, if you squint, probably you can see some details. I'm not able to see anything here, but then if you're displaying on a HD screen, you can probably see a little detail about the Spider-Man here, but then the image will look dark. However, in such a scenario, if you just increase the gain of the sensor, that is, instead of using very low ISO, if you're using a camera at a higher ISO, you will be able to get some detail out of the scene. So higher ISO essentially means you are basically running the camera at the highest. So here I'm using the camera at the highest setting. You cannot make the camera more sensitive at this point. Now, if I go a light level even lower, even at the highest possible gain, you wouldn't get any useful information from the scene. The SNR, which you get at this scenario, is really, really low, that you cannot get any useful information. Now, one possible solution to deal with this is to use a longer integration time. So that is, when I go from 30 milliseconds to 1.2 seconds at 0.25 lux, you will get good enough information from the scene. However, this is generally not preferred because if you are using a handheld camera, that may introduce camera shake, or if there is a moving object in the scene that is going to blur, that is going to get blurred in the image. Now, your cell phones sometimes, what do they do? What they do is, okay, before I get into that, so since if that is moving object at low light, the issue actually gets more pronounced. So here I'm taking images at 25 lux, and then I'm using an integration time of 30 milliseconds on the left. And you can see that that is motion blur in the toy at the bottom. To make sure that I'm able to get a sharp image of the toy, I should reduce the integration time. So I'm going from 30 milliseconds to 3 milliseconds. And I'm able to get a sharp image. However, the image becomes noisier because I'm basically reducing the amount of time I'm keeping the sensor open. So you may probably need to do a little denoising with the image on the right. Now, if I go to 2.5 lux, we are going to look at a, sorry. If you go to 2.5 lux, the image, the phenomenon of having very noisy image is going to become more pronounced. At this point, you have to make a decision whether you're going to deblur the image on the left or you're going to denoise the image on the right. In some scenarios, like on your cell phones, what they do is they will capture multiple 3 millisecond frames and then combine them to get a final good looking image. However, for example, let's say you are taking 10 images and your camera runs in 30 frames per second. It will take 1/3 of a second to generate a good looking image, which is generally not a preferred mode of imaging because you want to get the final image as fast as possible. Now, before we get into how to solve this problem, let me show a few examples where low light imaging is going to be useful. I'm just showing 3 of many possible use cases. The first one on the left is security in the dark. That is basically you are doing surveillance at night and there is no external illumination like the sun, and therefore the image you get is going to be extremely noisy. And if you don't, so if we go to the light levels that I mentioned before, it is again going to be, you cannot get any useful information. Similarly, for autonomous driving at night, when let's say you have a headlight, but then there are also objects on which there are no direct illumination. In such cases, again, you are going to be looking at such a scenario. For microscopy, sometimes you cannot use any powerful illumination on the specimen because otherwise you may basically destroy the specimen. So in all 3 scenarios, you are going to end up with a situation where you need to image at extremely low light that I mentioned here. Now, how have people been solving this problem till now? So if you go to Google Scholar and just type in low light imaging, you will get a lot of very famous solutions for this problem. However, if you just go to the main figure and look at the images in there, you will see a common thread. That is, they're looking at images which look dark. So their aim is to take images which look like this and then generate good looking images from this. But in most of the scenarios, in most of these papers, you can just use a higher gain. The camera, you just turn the gain to maximum, you will get some details out of this image. Or in some scenarios with these papers, you can just use simple histogram equalization and you will be able to get a lot of information from the scene. Now, that is not the scenario we are looking at here. We are looking at a scene where the image we capture has very low SNR, that even doing histogram equalization or the image is actually captured at the highest gain possible, that you cannot get, even at the highest gain, you are not getting any useful information. This is the scenario we are interested in. Now, how do we go about solving this problem? To understand how to solve this problem, we need to understand the noise model of the image sensor. So the sensor output here contains majorly of 3 noise sources. The first is the short noise, which comes from the randomness of the photoelectrons. The second is the dark current, which is spurious electrons which are getting generated because of thermal noise. And the third is the read noise, which is getting added by the circuit. So among these 3, the short noise is kind of unavoidable because that comes from the randomness of the photons itself. And that is basically nature and you cannot do much about it. However, the dark current and the read noise are a property of your image sensor. And then you would want these 2 to be as low as possible. So basically you want to use a better sensor where these 2 are almost close to 0. Now, I'm not a hardware person, so I cannot design image sensor. So what we do is basically go to someone who can make image sensors and get a better image sensor from them. So for most of the thesis, we use these image sensors called quantum image sensors for low light imaging. Quantum image sensors as an idea was proposed by Dr. Eric Fossum in 2005. They are supposed to be the 3rd generation image sensors, which replace the current CMOS image sensor, which is what we use in most of our smartphones. So the idea of quantum image sensor is that each pixel is going to be made up of tiny single photon sensitive jots. Now, each of these jots can basically detect whether there was a photon or not, which came and hit the sensor, that the noise is so low that you can make the decision. Because of this, each pixel can give a binary output, and because of the binary output, the sensor is actually fast because you just need to read binary data from each pixel, and because of this, the sensor is actually really fast. So this gives the sensor an ability to oversample. That is, when you're actually forming the image, you can sum up multiple pixels either spatially, or you can also sum up multiple frames to form a single image. And so the way you sum this up can be chosen based on the need. For example, if there is a moving object in the scene, you can sum up only lesser number of frames because summing up larger number of frames will give you motion blur. Now that is just one example. Basically, you can play around with it based on how you want to use the image sensor. Now, this was just an idea. So, since then, a lot of prototypes have been proposed. The prototypes can be broadly categorized into two. Ones which are based on single photon avalanche diodes and ones which are based on CMOS image sensors. So single photon avalanche diodes do avalanche multiplication. That is, what they do is whenever a photon is hitting your image sensor, the photon generates an electron, and that electron generates a few more electrons, and that electron keeps doing that. So you basically keep multiplying till till a large number of electrons are produced, and that's why it's called avalanche multiplication. And basically the detection is you have a comparator. Once the voltage in the sensor goes above a certain threshold, you say that was a photon. Now to do this, you need a very high operating voltage, and that very high operating voltage in turn means you get a lot of spurious avalanches, which means you detect a lot of photons even though there was no photons. Right. So these sensors also need a dead time. That is, once the avalanche happens, you need to reset the sensor, which takes a time before you can start using the sensor again. And the circuit for the sensor also takes up a lot of real estate, and that means the actual photon detection area is small compared to other image sensors. However, they do well with time resolution. That is, basically whenever the avalanche happens, I can basically say at this particular time instant, a photon hit your image sensor. And because of this, it could be used for applications such as time of flight, where you need to basically resolve when each and every photon is arriving at your image sensor. The second type is CMOS-based quantum image sensors. They are very similar to the current CMOS image sensors, which is basically used everywhere. If you are at all aware of the circuit diagram of a CMOS image sensor, it looks like the one on the right. So you'll notice that the capacitance there is the floating diffusion capacitance. And the major innovation of CMOS-based quantum image sensors is to make that capacitance as low as possible. That low capacitance means higher conversion gain, which in turn means lower read noise. Now, since
Abhiram, can you give us a simple explanation of what fill factor is?
Okay, fill factor is basically so each is the ratio of the photon detection area in your pixel.
Okay. Yeah, I know what you mean. All right, thank you.
Yeah. So SPADs do avalanche multiplication. That is, you generate a lot of electrons per photon. CMOS-based QIS don't do. So you get only one photon per one electron per photon. And because of that, you can actually count photons. That is, if you see 4 electrons, that means you actually received only 4 photons at your image sensor. Their operating voltage is low, and because of that, their dot current is also low, and their fill factor is much higher compared to SPADs. And here I'm just comparing a CMOS image sensor with the CMOS-based quantum image sensors and the SPAD. The few of the important things to notice are you can see the pixel size for CMOS-based QIS is much smaller than SPADs. Therefore, the resolution is larger. You have a higher fill factor for CMOS-based QIS. One place where SPADs beat QIS, CMOS-based QIS, is the frame rate. SPADs here I've shown up to 100,000 frames per second. It can even go larger, but currently the current prototypes for CMOS-based QIS can go only up to 1,000 frames per second. That doesn't mean they cannot actually go, but then the prototypes haven't gone much faster than that. And the read noise for CMOS-based QIS is 0.19 electrons, which is really, really small. The read noise for SPADs is actually 0 because they can give you only binary. There is no in between. They will say there was no photon or there was a photon. There is no in between, and because of that, the read noise is 0. However, they can give you false ones, and which means their dark current is larger. Now that the read noise for CMOS image sensors is 2 electron, which is really on the lower end of the possible read noise. So you need a really, really good CMOS image sensor to get a read noise of 2 electrons. they generally go up to tens of electrons. And so CMOS, as I said, since CMOS-based QIS can count photons, you can operate them in multi-bit mode. That is, you can use a few bits, while SPADs can give you only binary data. So, all right. We will be using the CMOS-based QIS, which is developed at GigaJet and Dartmouth College for most of the experiments that we do in this presentation. Now, we have a good sensor.
Okay, I have another question for you, Abhiram. So, so you have one of these GigaJet cameras, I guess, in your lab. Is that right?
Yes.
It's I assume it's not yet a commercially available product, or is it?
So the one which we have in our lab is not, but then you can actually get, you can go to the website and actually get an image sensor from them. They recently launched a 40 megapixel image sensor.
And how much what do they cost, and what's the resolution?
So astronomical figure. Because this is prototype, we haven't gone to the mass production yet.
Oh, okay. Okay. Thank you, Stanley. Okay, go ahead.
The resolution is 40 megapixels, and the price, I'm not sure. Price, I'm not exactly sure.
Okay, okay. Thank you.
So what we have seen is we can go and get a good image sensor. The question is that enough? Can I basically take the image sensor from my camera and then replace it with quantum image sensor? The answer is unfortunately no, because as I previously mentioned, there is still going to be noise from the photoelectrons, and it's a short noise and you cannot escape it. So I'm showing 3 images at the bottom of the screen. The first 2 are real images captured with the CMOS image sensor and a CMOS-based quantum image sensor. So I basically display the panda image on the screen, and then you have both the sensors sitting in front of the screen and capturing the scene. The light level is 0.25 photons per pixel, which is really, really low. And you can see that the CMOS image sensor has very little detail compared to QIS. QIS can give you a better SNR. However, if you compare QIS to an ideal sensor, so an ideal sensor is a sensor where dark current and read noise are 0. So we basically simulate an ideal sensor, assuming that the light level is 0.25 photons per pixel. You will notice that they do actually, the amount of details in those 2 images are really close. So, however, even the ideal sensor is extremely noisy. You cannot do much at this light level with just an image sensor. And therefore, you will also need better algorithms to solve this problem. And my thesis is a kind of combination of both, where we use better sensors along with image algorithms which are developed for these image sensors, so that we can do really good low light imaging. This slide shows a general overview of my thesis. I've broadly categorized it into 3. The first part is the basics, which gets into the basics of image sensor and how to model an image sensor. The second part are low light imaging applications. I have 4 chapters there: color imaging, dynamic scenes, deep blurring, and object detection. The solutions at this part can be, again, in a very high level, divided into 2. The first is understanding the noise model. So we basically take the problem, for example, color imaging. You do look at the Bayer pattern with the noise, Poisson noise, and then figure out how to do good demosaicing. The second is student-teacher learning, which is a learning scheme for deep neural network-based solutions. I probably wouldn't get into too much detail into this. I have a brief slide for all of these later. And the third part of the thesis is generalizing, where we ask the question: can QIS work only at low light, or can we also look at a scene which has low light and highlight and image at the same time? That is high dynamic range. And generalizing networks are when the noise level, when you want the same network to deal with multiple noise levels, how do you go about it? So with that, I'll get into a brief intro to each of these chapters. And these are all the publications that were made as part of the thesis, the first 3 are currently under preparation or in the review. The rest of these were published as part of TCI, ICCV, ICML, or ECCV generally. So these are the 2 papers which I'll get into detail today. The first is the exposure referred SNR for digital image sensors. The second is HDR imaging with quantum image sensors. The first one is currently under review. The second one was a TCI paper in 2020. With that, I'll go into a brief introduction to all the contributions. The first is low light color reconstruction using quantum image sensors. I have 2 papers. The one on the left is an Optics Express paper. So this one was the first color demonstration using quantum image sensors. The idea for this one was actually really simple. So at low light, you are going to get a lot of signal dependent noise, because of which you cannot use any existing Gaussian methods. So what we do is we use a technique called variance stabilizing transform, which transforms signal dependent noise to signal independent noise. And then we use a standard Gaussian demosaicing method based on plug and play ADMM to do the image demosaicing and denoising at the same time. And you can see some real results using quantum image sensors at the bottom. The one on the right is a deep neural network based method. So we do frequency selection there. The idea of that method is basically you take an image, you divide it into the 3, basically 1 Luma channel and 2 chroma channels. We notice that the noise in the Luma channel is much more weaker than the noise in the chroma channels. So therefore, we use features from the Luma channels to denoise the 2 chroma channels. Yes. Yeah, that is color reconstruction. The next is like dynamic scene reconstruction using quantum image sensors. This was an ECCV paper. So here we take a burst of images using quantum image sensors at extremely low light, and then we are training a network to denoise this burst into a single image. So the idea behind this is your network should deal with both motion and noise at the same time. Since it is really difficult at this extremely low light, the noise level is too high that the network can learn it by itself. We use a technique called student-teacher learning, where we have a motion teacher that can do motion alignment, and we have a denoising teacher that can denoise, and then use these teachers to teach the student network to deal with both motion and teacher at the same time, motion and noise at the same time. The next is computer vision at low light. So we have 2 papers here. The first is image classification in the dark using quantum image sensors. This is what I talked about during my preliminary exam. Here again, we use student-teacher learning to train our network to deal with extremely low light. We basically say replace the CMOS image sensor with quantum image sensor and use a network that is trained using student-teacher learning to do really good image classification at low light. You can see some real results, and I'm not sure if you can notice the difference in the image quality, but then you will generally notice QIS has better SNR than CIS, and because of this, that combined with our network can do really good image classification. The one on the right is object detection. Here again, we use student-teacher learning, but then we also do object detection on a burst of frames to be able to get features from a space-time volume. We use a module called non-local module, which can get these good features from a burst, and then we do object detection based on that. Again, we have some real results. You will notice that our method performs better than a faster CNN, which is a standard object detection method. The next is low light image deep learning. So the one on the left is a TCI paper, which is currently under review. What we do here is we propose an unrolled neural network based on plug and play ADMM to deal with Poisson noise, which you will see at extremely low light. We also collect some real data. That is, we have noise images along with the ground truth blur kernels. On the right, you can see the performance of our network on a couple of real images along with the blur kernels. The one on the right is a paper currently under preparation. I haven't made any figures, so I have just written down a bunch of points. The idea behind that paper is that so there are a lot of methods which can deal with Gaussian noise for deep learning. So let's say you have blur plus Gaussian noise. There are a lot of deep neural network methods. However, there are not a lot of methods which can do the same for Poisson noise. So basically, we take a bunch of these Gaussian deep learning methods and look what are all the qualities that you basically need to use for Poisson deep learning, and what are all the things you probably should. And we give you a few suggestions based on this.
Quick question.
Yes.
When you say you have a closed form expressions, what is that for? Some kind of theoretical limits, or a closed form expression for an objective function, or what is it? In the middle slide on the left is closed form expression.
Okay. Closed form expression means okay. So the Z one is a network.
Okay.
The blue Z update is a network, and closed form expression are just you can run it basically as a single go. So we basically have the V update is a Wiener filter, and X update is a quadratic solver. So both of which have really nice. So you can basically write down a single equation, and then it's for coding it, you will just have a small function which does that. And you don't need that. It doesn't have any parameters, or it is not iterative. That is what we mean by closed form.
Close. Okay. Thank you.
And the next one is a single network for multiple noise levels. So the idea behind this is, let's say you're training a denoiser. You usually train a different denoiser for different noise levels. For example, Gaussian noise of 25 over 255, you'll have a denoiser. 50 over 255, you'll have a denoiser. However, if you want to train a single denoiser which can deal with a range of noise levels, you will see a drop in performance, because, of course, at network, denoising a single noise level is going to perform better than a single network that is being trained for a range of noise levels. So now, so the black curve is a network which is trained at each individual noise level, and the blue curve is a network that is trained over a range of noise level. You will see that the gap between these two networks is actually larger at the lower noise level than the higher noise level. Now, what if that is not something you want? You want a more uniform gap. So this paper goes into how do you go about actually formulating this problem? How do you actually write down this problem? And what are the solutions we can use to solve this problem?
So is the answer to your question of your paper yes? We can train one denoiser for all noise levels?
based on if you know what you want out of your denoiser.
Okay, yeah, I was just being facetious about that. Yeah.
Okay, so that.
Well, I have a similar question. Go back. Sorry, Abraham. So you say you have a curve there that says our goal. So the question is, have you achieved that yet, or is that still something that you're hoping to achieve?
We have achieved that. If you look to the right, the blue line which we have is this red goal.
Okay, that's the uniform. Okay.
The color coding probably is really bad, but then the blue matches to the red here.
Okay. All right. Thank you.
Yeah. Okay. So with that, I'll get into the main part of today's presentation, which is high dynamic range imaging using quantum sensors. So the question we asked, yes, as I mentioned again, it is based on these two papers. Okay. So I have shown before that image sensors struggle at low light. Now, another place where image sensors struggle is when you have a range of noise levels in a range of light levels in the same scene. For example, the image on the left, you have a range, you have light levels going from 25 lux to 25,000 lux in the same image. The indoor is the light level indoors is low, the light level outside is high, And because of this, the outdoor image looks saturated and then flushed out. This doesn't mean that the camera cannot capture the outdoor scene. If I just want to capture only the outdoor scene, the camera works fine. It is the range in the same scene that is causing the problem. This range is called the dynamic range of the scene. So you have a very large dynamic range, and therefore your image sensor is struggling to capture both of these light levels at the same time. And this problem shows up even when you reduce the light levels. So 25 and 25,000 lux, basically if I divide both of them by 100, you will still see the same problem. So this is not a very particular problem that shows up only at high light or only at low light. So as long as the range is large, your image sensor is going to struggle. The question we ask is, we have seen that QIS works at low light really well. The question we ask is, can QIS work for high dynamic range imaging too? In first glance, it will look as if the answer is no, because here I'm just showing two images. The image on the right is a CMOS sensor. The image on the left is a single bit QIS. And the light level is, you are getting, the average light level is 10 photons per pixel. And since you are using only single bit, the quantum image sensor image is going to look really washed out because we are basically anything greater than 1 photon QIS cannot, we are assuming here that the QIS cannot count. However, we haven't used an important property of QIS, which is oversampling. So oversampling is where you capture multiple frames using quantum image sensors. So by the time a CMOS image sensor can capture a single frame, the QIS can capture a lot of frames, sometimes even hundreds of frames. So if we use this property of QIS and obtain an image, the previous lamp image will look something like this. So basically I'm capturing 4,000, I'm assuming that over a time interval, we are getting 10 photons on average. And I'm using a single exposure for CMOS image sensor. And then I'm basically dividing this time interval into 4,000 equal blocks. And then I'm using 4,000 QIS frames to get and sum them up to get the image on the left. The question that becomes difficult to answer here is, how do we compare these two? For when we get only one frame and we have two different cameras, it becomes really simple to compare. You just look at their read noise, you just look at their dark current, whichever one gives you a lower read noise, whichever one gives you a lower dark current is a good image sensor. However, when I have 4,000 frames for one and I have only one frame for the other, how do we compare these two? Now, one way of doing that is looking at the mean camera input. What do I mean by this? So consider this following scenario, which I have described here, which is I'm assuming that a CMOS image sensor has a full well capacity of 4,000 electrons. So that means if you're getting 5,000 photons, the image sensor will still give you only 4,000 electrons. Now I'm assuming that QIS can operate 4,000 times faster. So QIS is capturing 4,000 single bit frame at the same time. And the integration time of QIS is 1/4,000 of the CIS. So therefore, the total integration time for both QIS and CIS is the same. Now, if I look at the mean output of the image sensor for CIS and QIS, it will look like this. So for CIS, the mean signal output is a very linear line, which goes linear till saturation. And then once you reach saturation, it kind of becomes a horizontal line. That probably is a little non-linearity here, which is not getting captured here because of the scale of the axis. But then this is how it looks like. For QIS, the curve looks something like the one on the bottom, which is extremely nonlinear. And it takes a lot of time to reach saturation. So this part of the curve, so you basically, CIS can count only up to 4,000 electrons. And then just because you're doing more sampling, you are able to get some signal here. This part is called overexposure latitude. What this means is basically your sensor is not saturating, and therefore if the sum of 4,000 frames is 3,500, I can basically go and say that the exposure was 8,000 photons. So you can make the decision, and that is much larger than the full world capacity. And this phenomenon is called overexposure latitude. And then from this curve, it will look like just by oversampling, you are getting a larger range. Almost from 4,000 photons, you're able to go to 14,000 photons. However, we are missing an important part here, because we are talking just about the mean, and then we are not talking anything about the noise. It could be that the signal at 3,500 photon, the mean is 3,500, but then the noise is 1,000, and then you actually cannot get any useful information at that point. So this curve is useful to some extent, but then it doesn't tell you the entire story, right? So another way of looking at this problem is to look at SNR. So SNR is usually defined as the expected value of the signal over the standard deviation. Now, this is not the only form. You can use various varieties there. I'm just using one of them, which is expected value of y over the standard deviation. Now, for example, if y is drawn according to a Poisson random variable, you will get this SNR will be square root of theta, where theta is the Poisson parameter. And in a log scale, you will get a really nice linear line. However, this has a problem, because think about what happens when we introduce full world capacity. So as the number of photons crosses the full world capacity, the variance of the signal keeps going down. So as you keep crossing the full world capacity, the variance actually goes to 0, and this SNR expression, this particular SNR expression, actually goes to infinity. So this, however, we know that as you cross the full world capacity, we actually don't have any useful information, because all you are getting is saying is the light level is over the full world capacity, and you don't have any more useful information. So this is a bad measure. Now, what people generally do in image processing is to use a heuristic, which is we replace the SNR which we saw before by another expression, where the SNR goes to 0 once you cross the full world capacity. So basically what they're doing here is cut it off here. Once the theta goes above the value, the SNR is 0. Now, we may not know if this is a really good, very good expression, but then for this range of light level, till you are very close to the full world capacity, it is right. And then people generally don't care what happens after you reach the full world capacity. So this is a very good heuristic. Let us use this heuristic for a single bit QIS. So I'm defining a single bit QIS this way. So you basically have Poisson. And then when the number of photons is greater than 1, anything greater than 1, your output is 1. And anything less than, if it is 0, the output is 0. Okay. Now, so the new heuristic will look like the one on the left. And you remember the curve. So remember what the scenario was, what the assumptions was. So QIS is operating 4,000 times faster. That means I'm summing up 4,000 single bit QIS frames. So for each of those frames, for theta greater than 1, your SNR is 0. Therefore, when you sum up 4,000 frames, for theta greater than 4,000, your SNR is 0. So that means anything over here, the SNR is 0, which again doesn't tell us is not the right thing, because we know that there is a non-linearity there, and then the SNR probably the SNR could be really poor for all we know, but then it is not 0. There is some SNR there, but this is not capturing that. So one way to again deal with this is to use what is called as the exposure referred SNR. Now the SNR which I defined before is called the output referred SNR, because there you are calculating the SNR with respect to the output of the image sensor. What the exposure referred SNR is doing is calculating the SNR with respect to the input, which is theta. So this is what we deal with in this paper. Now, by no means this SNR expression is new. This has been used for decades to deal with nonlinear image sensor. What we do in this paper is to get into the statistical properties of the SNR and what are the estimators for which such an SNR will hold good. Now, one possible explanation for where the exposure referred SNR is coming from is from circuits. So it is generally referred to as input referred SNR in circuit analysis. So basically, when you do small signal analysis, small signal gain analysis, the d theta over d expected value of y, which is, so if you assume expected value is the output and theta is your input, d theta over d expected value of y is the gain, and you do some math based on the gain, you will get an SNR which looks like the one on the top, which since we call theta as exposure, therefore it is called as exposure referred SNR. Now, if we take this expression,
I'm sorry, Abraham, can you explain again what theta or theta as you're calling it is?
sorry.
What is this theta?
Okay,
Or
so
theta.
theta is the mean number of photons. So that is you're getting light based on a Poisson process, and the Poisson has a parameter. That is your theta.
Yeah,
right, thank
I
you.
actually had the same question, which is, so what are the units of y and theta?
Okay, so Y is number of photoelectrons.
Okay, so y is charge.
Yes, yeah. Y you can think of Y as voltage or charge. Yes.
Okay, well, they're a little different.
Yeah. Okay. So in this case, Y is number of electrons. It is not charge. It is the number of photoelectrons. So it will be charge divided by charge per electron.
Right, okay, number of electrons, which is equivalent to charge. And then
Yes.
theta is photons.
No, theta is not photons. Theta is the flux. So theta is the mean number of photons that is arriving at your sensor. Theta is the parameter which defines the number.
But the units are photons.
Yeah. Yes, I guess that's right.
Okay. All right, so it's this thing has units of photons per coulomb or something like that. Okay, or electrons. All right. Right.
All right. So so in this slide, I'm basically comparing output referred SNR with exposure referred SNR for single bit QIS. Note that I'm defining the single bit QIS a little different. Before Q was 0. Here you can choose your Q based on how you want to use the image sensor. So what basically Q is basically if the threshold. So if it is more than certain number of photoelectrons, you say this output is 1. If it is less than that, you say it is 0. Now you can notice that the SNR has, again, it is going to infinity for single bit QIS for output referred. However, the exposure referred SNR has a behavior which we would expect out of an SNR, because it basically goes up, and then once this signal starts saturating, which is first QIL basically at around 1. If Q is 0, once it starts once it goes over 1, it needs to start going down. So exposure referred SNR is a good, basically this curve says it is showing the behavior which we wanted to exhibit. So the nice thing about exposure referred,
Abraham, I have a question on the previous slide.
yes,
So it says here y is distributed as Poisson with mean theta at the top.
yes.
But wouldn't there be, I mean, so theta is units of photons, right? And y is units of electrons. So wouldn't there be a proportionality constant? Isn't that exactly what that?
Yes. So here I'm assuming that there is no proportionality constant. Generally, there will be quantum efficiency, which will define your proportionality constant.
But you can get many electrons per photon, right?
No, you can get only one electron. Photoelectric effect basically says one photon can generate only one electron at max.
Oh, really? So you only get one electron?
Yes. So each photon, you may get an electron or no electron. that has a probability. But then if you assume that probability is 1, then for each photon you will get an electron.
When you get that one electron,
Mhm.
I guess this, I mean, maybe I'm jumping ahead, but this is going to, but one of my questions was I had written down here was that, is the output of this QIS, I've always been a little unclear about this, is the output digital or analog?
So usually what happens is there is a boson and then there is a read noise to it, right? So Y will generally be analog because it's a boson plus a Gaussian, which will give you.
I mean, the actual device.
Yes.
The
So
output is digital. I mean, is there a thresholding that occurs in a digital logic gate that just specifies a 1 or a 0, or does it actually pass on an analog voltage?
The device itself will give you digital output. So Z is what you'll get out of the image sensor.
Okay, and when you measure this one, so you actually measure a single electron, the charge associated with a single electron, or there's some kind of amplification process?
Yes. Yes. Let me see if I can get that figure.
I mean, the
Yes.
thing that's confusing me, I work in photons. My photons usually have much, much higher energy, right? So usually what happens is you have like a single photon, and then as a function of its wavelength, you get a lot of electrons, and the electrons can vary. Basically the charge you get can vary depending upon the wavelength of the photon, or the energy of the photon. But you get like a pulse. You know, in standard kind of photon counting things, you'll see like a little voltage pulse that comes out of the amplifier, and then you just put a threshold and you say, oh, look, an event occurred. So, but you're saying you get like one electron?
Yes. Okay. So I need to go back a little further back. Let me go back.
Yeah.
SPADs and CMOS based QIS, right? Okay, so the one on the left are SPADs. So what you described will exactly happen here. So one photon will start an avalanche that you will see a really large spike.
Right, so you get many electrons.
Yes. But that is not one photon generating many photons, but then many electrons. One photon generates one electron, and that electron generates a lot more.
Mm-hmm.
Right. So therefore, an event of your photon arriving at your image sensor will have a lot of electrons. However, for a general camera in your image in your cell phone, those cameras, you will get only one electron times 1 electron per photon, and then so you will have a conversion gain. You basically read the voltage. So your pixel basically accumulates a lot of electrons, and then that will create a potential difference. And then you go and measure what that voltage is, and based on that voltage, you basically figure out, okay, I got these many electrons. So now each electron, so that is usually a conversion gain, which means this voltage can be only a function of, so if there are 5 electrons and my conversion gain is 1, you will get 5 volts. So in CMOS based QIS, each photon is generating one photon is generating 1 electron, and there is no this multiplication effect. So what they are really good at is, most of your cell phones have very, very high noise that you cannot actually figure out how many exact photons were there. So basically what will happen is there will be 5, let's say 10 electrons, and then your read noise will be so large that it will have another 10 electron spread that you cannot say exactly how many photons were there. However, CMOS based QIS makes that noise really small. As I said here, that spread is just 0.19 electrons for CMOS based QIS, if you notice here.
Which I can't say what you're pointing to because.
Yeah, no, I'm not able to do that. But so the read noise for CMOS based QIS, it's the third row from the bottom for CMOS.
Read noise, okay.
Yeah.
So you're saying the read noise is 0.2 electrons.
Yes, that is really small. So that is the spread of voltage on top of your number of electrons.
Okay,
And since that is really small, you can say exactly how many photons, photoelectrons are there collected in your image sensor.
mm-hmm. Okay, thanks, that is very helpful. But then it's digitized before it's read out.
Yes, yes.
So it's thresholded as part of the logic in each gate.
Yes. So basically, as I'm showing here, you will get photoelectrons, darker, and read noise, and then there is an ADC generally.
But the ADC is 1 bit.
Yes, yeah, for single bit QIS, yes. You can use QIS in other bit modes too, but then if you're using it in single bit, yes.
Mm-hmm. Okay, thank you.
Yes. Yeah, so you generally can get nice closed form expressions if I'm not assuming any complicated read noise. That is, if I'm assuming Y is just Poisson and then an ADC. So this is single bit and this is multi-bit. You will get some closed form expression. However, when the noise model becomes more complicated and then you want to add other factors into the noise model, it is really, really difficult to get a closed form expression for exposure deferred SNR. However, you can do Monte Carlo simulation. So here we are looking at what happens when we add read noise to the noise model and when we add dark current. So you can basically run Monte Carlo simulations to estimate what the variance is and what the derivative term is. And then based on that, you can basically estimate what the SNR curve looks like. Now, since we can plot an SNR, let us go back to the previous curve which we had, and let's look at what the SNR curve looks like now. So I'm mentioning what the assumptions are. So this is the noise model. So you have Poisson times, this should be theta. It shouldn't be alpha times x. It's Poisson of theta plus normal of 0, sigma read. So that is the read noise. So these are all the assumptions. The read noise for CIS is, I'm assuming it's 2 electrons. For QIS is 0.2. The full well capacity for CIS is 4000. For QIS is 1. That is basically the thresholding, which we do Q is equal to 1. The number of frames for CIS is 1, and for QIS it is 4000. And the ADC for CIS is 14 bits, and for QIS it's single bit. Now, with these assumptions, if we plot the SNR, this is what the curve looks like. Let us look at the curve in a little more detail. Now, remember that theta is the mean number of photons. That is, theta is directly your light level. Now, we have mentioned a lot of times till now that QIS is really good at low light imaging. But then from this SNR curve, it looks like CIS, which is the green curve, actually does have better SNR than QIS at low light. That may sound very counterintuitive. However, in most of the results which we saw before based on low light, that was a catch, which I of course didn't mention, was that we use only very few number of frames. So for color reconstruction, we use only 10 frames. For lower dynamic, we use only 8 frames. For computer vision, we use a single frame or 8 frames. So when you use large number of frames, you get a phenomenon which we call the accumulation of read noise. So assume a fixed time budget, and then I'm dividing the fixed time budget into, in the top case, I'm dividing it into 100 frames. And in the bottom case, I'm dividing it into 1000 frames. And you will notice, at least, I'm not sure if you can see it in the screen here, but then the image on the bottom actually is much noisier for when the read noise is 0.25 compared to the image on the top. Now, why does this happen? Let us look at the equation here. So your image, so each frame of your QIS is basically simulated according to this. So it is an ADC, and then you have a Poisson since a fixed budget is there, I'm assuming over the entire budget is alpha time x. Now, if you use only one frame, t is 1. If you use 100 frames, t is 100. And then I'm going to sum t such frames. If I ignore the ADC, the sum of y will have this form, which is the Poisson. You know that when you add multiple Poissons, you will end up with another Poisson. However, the read noise adds up. The read noise adds up, which means the overall Gaussian noise is now t times sigma read. So the more t you use, the more read noise you get. And that is why the curve has this weird gap. Now, when I use a smaller t, you will notice that QIS is in fact performing better than the CIS. However, it falls down really fast because the lesser frames you use, the dynamic range of QIS is small.
Abhiram, I have another question. If you could back up just to make sure I understand this. So is the Y before or after the thresholding? It's before?
Now, generally, Y is after thresholding. For the sake, just to show what, so if you ignore the ADC, I'm just showing to see what the effect of read noise is.
Oh, okay, but the read noise would not add in the same way if it was after thresholding.
Yes, it wouldn't add in the same way. Yes, that's right. And
I mean,
I
you
just
would-
need an explanation as to the possible explanation as to why that is happening. The actual expression will be much more complicated, and then it will be really difficult to actually point out where the noise is showing up from.
I mean, what would happen is you'd have some probability of a false alarm, essentially, if it's after thresholding and it's fixed. So you'd have essentially sort of a background plus on.
So the issue is this, right? It is difficult to differentiate between which of the signal, what is happening because of Poisson, because the Poisson itself is random, and then you have a false alarm on top of that.
Right. Yeah, I'm not sure how I feel about this one expression here. You have Poisson of alpha times x over t, but it's not really Poisson because it's an analog quantity that comes out of there.
No,
It's not Poisson, and so you actually just threshold it.
No, the analog. So the analog signal is Poisson plus the read noise, right? And usually
Okay, I guess you can model it that way. Okay, so you're saying it's Poisson because the number of electrons that come off of there is discrete, proportional to the number of photons, and it's that you're sort of, it's Poisson times some analog constant.
Yes. You are right. So what usually happens is so Poisson plus read noise, and then there is a conversion gain, which is a factor sitting in front of that.
All right, but what happens? Okay, I'm sorry. Okay, if you have different wavelength photons, so you always get exactly one electron with the same energy. I mean, I guess you transfer an electron as a quantum, but there's no, I mean, I still feel like there would be some kind of residual effects associated with, there's some analogness in there maybe, but maybe not. Okay.
So at least from my understanding, how it works is irrespective of your energy of the photon, as long as it is above the certain threshold, each photon can generate only one electron. However, the probability with which they are generating varies over wavelength.
Okay.
I'm not sure. So probably.
Okay, yeah. Okay, so the probability of the event occurring can vary with wavelength, but when the event occurs, it's always exactly one electron.
Yes.
And there's no, okay, all right. Thanks.
Yes. So as I said before, as we go from 4,000 times faster to 10 times faster, you will notice that QIS actually performs better at low light, and this is and the one on the left, right is what we use for most of the experiments which we saw in low light. However, when you use the fast mode of QIS, you will look, you will get a performance which looks like on the left, and you will actually lose out on low light. However, the overall dynamic range, so I define dynamic range as, so the range of theta for which the SNR is greater than 1 or like 0 dB. So if I define the dynamic range to be that, you will notice that the dynamic range of CMOS image sensor is 64 dB. However, for quantum image sensors, it's actually 74 dB. So it more than makes up for what it loses in the low light in the highlight region. So you are able to get much better dynamic range. You are almost able to get 10 dB dynamic range from quantum, extra dynamic range from quantum sensors. However, we made an important assumption before, which is we are assuming QIS is actually 4,000 times faster, which may not always be the case. Now, let's say QIS is only 500 times faster. This is the curve we get. But from this curve, without even me actually measuring it, it looks like the dynamic range of QIS and CIS is the same. So what is the advantage of using QIS? And QIS, in fact, has a lower peak SNR compared to a CIS, right? The another catch here is that we use, so in the previous experiment, we use the same exposure time for all the 500 frames of QIS. However, we can use what is called as exposure bracketing. What exposure bracketing is, you basically, instead of using all the frames to be having the same exposure time, I'm using a different exposure time for each frame. For example, here I've divided, so 480 is close to 500. I've divided 480 frames into 3 possible exposure time. One is 1/480 times 30 milliseconds. I'm assuming CIS is doing 30 milliseconds. So 1/480 times 30 milliseconds is the longest exposure time. The second is 1/10 times 480. So that is 1/10 of that. And then the next one is 1/100 of that. Now, if I use this, these exposure times, the curve I get will be the one in the middle.
I'm sorry, Abhiram. What are the red dots on the previous slide? Are those readout timed or something?
Oh, the red dots. Okay, I should have. They're just photons. They're supposed to be randomly generated photons.
Oh, okay. Thank you.
Yes. So by using exposure bracketing, you are able to get dynamic range. However, notice that it comes at the cost of the peak SNR. So the image on the left, you are having close to 25 dB SNR. However, the image on the right, the peak SNR is close to 20, and then it even goes down when I go from 3 exposure to 4 exposure. So you are able to increase the dynamic range, but then that you need to sacrifice a little of your SNR. So what that means is your image is going to look much more noisier, and then you probably need to do a lot more processing to get a good looking image from these data. But however, you have signal. The SNR for CIS in some cases is 0, like it's really low, but then we are able to get some SNR, but then you need to do some further processing to get your final image.
Abhiram, I'm sorry to have to ask this question.
Yeah.
Would you go back to the previous slide just to follow up on Jan's question to make sure I understand this? What are the green things?
They
I
are
was probably
the
daydreaming.
exposure time. They are the exposure time when the shutter is on. Shutter of your image sensor is on.
So is that? So why is the shutter on and off? Is that a okay? Does this involve dead time or no?
No. It has nothing to do with dead time. So
Okay.
what we're doing is, let me.
Oh, this is for exposure bracketing, you're saying?
Yes.
Oh, this is so you can control the amount of light that comes into the sensor, you're saying?
Yes. So basically, as I mentioned here, so here you have your sensor. you basically start counting. Let me tell in terms of electrons, right? So you start counting, and then you turn your sensor off, read the data out, and then you turn the sensor on again for each time it is on and off.
Mhm.
So you basically have your sensor on for some time and then read the data out. So by the time all the electrons are read out, now you start counting again. So that is that amount of time for which your sensor is on is your exposure time.
Okay, so this accounts for what the practical readout time of the logic is.
Yes, this is so basically, so in your image sensor, there are two different things, right? One is your readout time, the other is your exposure time. So you can have your sensor exposed for only 1/100th of a second. However, you can run your image sensor only at 30 frames per second. So that it could be that, so basically your image sensor, the exposure time is only 10 milliseconds. However, it takes 30 milliseconds to read the data out. They are two different things.
Yeah, no, I understand all that. Did you use, for the plots you're giving, are you using practical values of the readout time and for that sensor?
Okay, so that in some sense, yes. So the thing is, for CMOS based QIS, as I said, it currently can go only up to 2000 frames per second. However, if I go to SPADs, I can go up to 100,000 frames per second. Now, 100,000 frames per second is I'm assuming CIS runs at 30 frames per second. So I'm basically assuming the CIS runs at 30 frames per second. Mm-hmm. So that means I can go up to 3,000 frames for every CIS frame. I can go up to 3,000 QIS frames for every CIS frame. Here, I'm just assuming 500. So that means I'm assuming 15,000 frames per second, which although a prototype, a QIS, CMOS-based QIS prototype doesn't exist that they can do this, but then it is entirely possible.
Mm-hmm. Mm-hmm.
Yes, so you get basically by doing exposure bracketing, that is not using the same exposure time for all the image sensor, you can get a larger dynamic range, but then you sacrifice the SNR. QIS also has, using exposure bracketing with QIS also gives you another advantage that, so as I said, CIS, I'm assuming runs at 30 frames per second. You need to wait until 33 milliseconds to give you an image. However, since QIS is much more faster, you can get an estimate HDR image much faster than a CIS. The image will be extremely noisy. However, you will get an estimate HDR image, which is what I'm showing here. So even at as low as 1.8 millisecond, that is close to 15 times faster than a CIS, you will be able to get a pilot HDR estimate. And if you use if I have a longer time budget, CIS will be able to do much better. So at 90 milliseconds, the CIS quality will be actually better than QIS. However, when the time budget you have is smaller, you will be able to get a quick HDR estimate with QIS. Now, one thing I've not shown here is I've given you exposure bracketing. I haven't actually shown you how you go from all these frames to these images, which I have shown at the bottom here, which is what I'll get into next, which is how do you actually do HDR reconstruction. That is, I have a bunch of these binary frames, which I captured at different exposure time. How do you actually reconstruct it? So the idea is basically this. You capture a lot of these frames at different integration time. So I'm assuming a static scene. I'm not going to get into how to deal with motion while doing this HDR image. So you basically divide them into based on their integration time. So you put all the short integration time together, all the medium integration time together, all the long integration time together. So the idea is you sum them up and then you linearize them. Now, what is linearize? As I mentioned before, the mean output from your image sensor has a very non-linear curve. Linearize basically means invert the curve. So, for example, if the exposure is, if theta is 120, here when I use 100 frames, the mean output is actually 70. So when I get 70, I basically say my theta is estimated to be 120. And you linearize, and you can actually show that this is the maximum likelihood estimate for single bit QIS, according to this paper by Dr. Chan from 2016. So you sum these frames, each of them separately. So basically you sum all the short exposure frames, you sum all the medium exposure frames, you sum all the long exposure frames, and then you linearize them. And then we pose a question, what is the optimal way to linearly combine them? So that is, we give a weight to each of these exposure, and then we are saying, we are asking the question, what are all the weights? So we formulate that problem as, so your estimate is a linear estimate, which is you basically multiply each of this exposure with a weight W, and then we want to maximize the SNR of this linearly combined image. So we can, so that optimization problem is written like this. So you basically want to maximize the SNR with some constraints on your weights. That is, the weights should sum up to 0 because for each, basically you are linearly combining them, and then your weights should always be greater than 0. So you do a little math with this. It's really simple maths. You will end up with the weights which are directly proportional to the square of the SNR. So what it says is I basically need to find the SNR for each pixel and square them, and then where the weight for that pixel at that integration time is proportional to the square. And so since we actually don't know what the SNR is, because the SNR is a function of your ground truth theta, and we don't know what the theta is, what we propose is to do an iterative method. So you first estimate what the ground truth is, and then based on the estimate, you calculate the SNR, and then use that SNR to again update your ground truth image, and then keep doing this on the time. Yes, so I'm showing some results here. We are comparing our method with 2 other methods. I'm not even sure you can see the details here, but then you can at least see the log mean square error which we are using, which is basically, since HDR, you generally cannot write the image 0 to 1. You basically have a wide range. You convert it into log scale and then calculate the mean square error. You will notice ours perform better. So the other 2 methods are actually, one of them uses simple sum. So you basically sum all of the frames. The second is use output referred SNR instead of exposure referred SNR. And our method is using exposure referred SNR. And there is another set of results here comparing using output referred SNR and exposure referred SNR. You will notice that we have very less, the amount of artifacts in the extremely bright region is lesser for using exposure referred SNR compared to output referred SNR. And we also have some real results comparing the 3 methods. So the simple sum kind of washes out the details in the dark. So these are all captured using a real QIS. So we use 30 frames, and we divide it into 3 exposure times, and the exposure times are given at the bottom: 75 microseconds, 375 microseconds, and 1875 microseconds. And then, so the output referred SNR gives some really weird effects in the brighter region because it is not able to sum them up correctly. It is not able to weigh them correctly, and then our method gives you a good reconstruction. And the one on the top, we are actually showing, what we are showing is even when use only 20 frames, you can get a much better dynamic range than a CMOS image sensor. It could be much more noisier, and then it looks really washed out compared to a CIS, but then it actually has better dynamic range than the CMOS image sensor. And then at the bottom is another set of results using our proposed method. So what have we seen till now for HDR imaging? So first, we saw that we need to use exposure referred SNR for analyzing the image sensor. We have also shown that oversampling helps QIS for dynamic range. So, and then we have shown that exposure bracketing extends this dynamic range even further. And we have seen that QIS helps in really fast HDR imaging. And we also proposed an optimal reconstruction method for quantum sensors. Now, let me get into the overall summary. We have seen that QIS is great for low light imaging. We have seen that QIS is great for HDR imaging. However, not at the same time. So basically, you need to choose when you want to use QIS for low light imaging, and then when you want to use QIS for HDR imaging. Now, one thing we haven't gotten into too much detail is QIS is actually great for motion too, because you are actually capturing a lot of frames. When there is a fast moving object, the motion information is encoded in your data. And we haven't gotten a lot into it. And then we haven't actually studied the interaction of motion with the other two. We have seen how low light imaging and HDR imaging compares. We haven't involved the interaction of motion with these two. And so as we said, for low light and HDR, you need to decide the mode of operation based on the need. And we have talked only about exposure time, but then there are a lot more parameters to choose from. We have frame rate, width, depth, exposure time, and sensor gain. And so this is how currently imaging is done. You basically have a black box. Your cell phone gives you an image, and then you take those images and use it for whatever purpose you want to use it for. And there is some control with your camera, but then it is all defined by the camera manufacturer or your cell phone. However, when you go to QIS, there is a lot of parameters you can control. And these parameters need not be like, you don't need to use auto exposure. Probably you can use it based on the application you want to use it for. For example, you want to do object detection at low light, you probably, instead of maximizing SNR, you can actually maximize something else, which could be defined by you. So that means we are moving from a black box based cameras to what, this is not a term I use, but I heard someone else use it, which is a really good term, which is software defined cameras. So QIS gives you a lot of flexibility towards achieving this goal of software defined cameras. So that brings me to the end of my presentation. I would like to thank everyone I work with, the companies I've interned and the sponsors. I'd like to thank Dr. Chan. It's been really fun working with you, and all my collaborators, without whom none of my papers would be possible. And this doesn't even include everyone else in the lab, the discussions with whom made most of this work possible. So thank you. And that's all I have.